All right. So let's look at these systems. We have spring, we have damper, we have mass. So it's dangling around, so it's a rotational motion. So let's see, we need to find what's on the left-hand side, right? So left-hand side is T minus U. Your T is kinetic energy. In this case, is a rotation. And then what is the J? We can ignore the mass of this wire. And J is just simply a mass dangling around a joint, and then distance is L. All right. So your potential energy, in this case, it actually have two parts. The first part is due to the spring. So let's say this displacement is x, and then half kx squared. That's the potential energy due to spring. And then the second part is the energy due to the gravity.
Hey, Professor, I had a quick question.
Mm-hmm.
So you were talking about so can we scroll back up one page real quick?
Yep.
Sorry, back up to the notes, sorry.
Okay. Mm-hmm.
So the two x dots that we have for the relative motion, is one of them like, so if we had a spring and a dampener, is the x dot 2 say like that's the dampener and x dot 1 would be the spring, or?
Okay, I can use an example to show you what's the relative velocity mean. So you can see that that's the damper, right? So you first find out all the nodes of your damper. In this case, you have nodes O1 and O2, right? So the relative velocity, let's say, let me use a symbol y there. The velocity y is just the velocity at O1 minus the velocity at O2, because in first degree of freedom system, one of the nodes is going to be stationary for sure. So in this case, your node O2 is fixed, so it's directly x01 dot. So that means your relative velocity is directly the velocity of this node.
Oh, okay. And so in like other systems where we have more degrees of freedom, that,
Yeah.
say that node might not be stationary.
Yeah, exactly. I can give you an example. Like you have mass number 1 and mass number 2. So that's your K1, K2, and K3. And then that's your damper, let's say that's C. In this case, because you have a two mass, you need to use two coordinate systems, right? X1 and X2 to describe the motion. So that means the degree of freedom is 2. So let's look at these C damper here. So in order to find the R, is half C, but then again it's going to be X dot relative. So in this case, it's going to be half C x1 dot minus x2 dot square. Make sense?
Yep.
Okay. Yeah, you're not going to see these systems for a while. That's actually in almost to the end of semester. You're going to see these during your Thanksgiving. Okay. So let's look at this. We have a spring, and then we also have gravity. So again, because you can pick either point as your initial, as your reference point. Let's pick the lowest as a reference. Then it becomes plus 1 minus cosine theta times the total length is L times mg. All right. So that's your potential energy, and then you can write it down. Your L equals to T minus U, and then that gives you half mL squared theta dot square minus half kx squared minus 1 minus cosine theta mgl. And because we don't want to see both x and theta in the system, so let's go back to the geometry. We know that x is sine theta a. Oh, sorry, sine theta b. All right, so once you have this, then you can replace it. This becomes b squared sine theta squared. And then let's just go back to the Lagrange's method. We need to calculate partial derivatives with respect to velocity. And then that gives you ml squared theta dots. Then we need to calculate one more time derivative for these partial derivative. So constant states, single dot becomes double dot, which means velocity becomes acceleration. And we have to calculate partial derivative with respect to position. So that gives us minus kb squared sine theta cosine theta. That's for this term. And then we have to do it for the second term. So that's, let's say, that's minus sine theta mgl. Because minus cosine theta becomes sine theta, and then there's a negative sign in front. And then we can plug everything back into the Lagrange's method equation, and then get what's on the left-hand side. That's ml squared theta double dot, and all the positives are gone to become positive. All the negatives are gone, and they become positive. That becomes kb squared cosine theta plus mgl sine theta. And then we already get what's on the left-hand side. As you can see here, we never look at the damper when we calculate about the left-hand side expressions, okay? So then let's deal with the damper. Again, we need to find the Rayleigh dissipation function first. So that's just half times the damping coefficient times the relative velocity. In this case, as I said before, it's just single y dot square. And then what is y? According to the geometry, it's just a sine theta a. That means your velocity is sine cosine theta times a times theta dot. You do a time derivative on both hand side, and then you get the velocity. So that's how you get your r. Your r is half ca squared cosine theta squared theta dot squared. All right, so we need to find your qi. Your q is minus partial r, partial velocity. Okay, so because we're doing partial derivative for theta dot, so whatever in front, they have nothing to do with theta dot. We consider it as a constant. So that means it becomes ca squared cosine theta squared theta dot. And remember, there is a minus. So you can plug this q back in. That equals to q equals to minus ca squared cosine theta squared theta dot. So that's going to be a final solution of equation of motion. And then if you assume small angle, that means sine theta is about theta, cosine theta is approximately 1. And then you can plug everything back in. You have ml squared theta double dot plus kb squared plus mgl theta plus ca squared theta dot equal to 0. And then you're having a linear solution.